Today we will discuss the solution of the test exercise on synchronization. What is the most important element of the solution? First, identification of resources that are in conflict. Second, the manner of getting those resources. Third, the manner of releasing the resources, which is mutual scheduling of processes. First, identification of resources. Many students assumed that this exercise is similar to the road cross. However, let's look. First, let's look at the crossroads. Why we divide the crossing into 4 fields? Because a process that drives straight has a new candidate for getting this resource. A new conflict arises. Here it is the conflict between this one and this one. Here, one additional process is added to the conflict. That's why we separate those 2 resources. For this, only those. For this, additionally, this one. Let's look at the narrow part of the street. If I get into this part of road, here and here and here, no new car comes from left or the right side, or from the air, or from the background. So my picture that I have drawn on the screen, on the blackboard, I intentionally showed where is the resource on which we have the conflict. We can have many lines. We don't know how many. It's not important. And the cars from those lines want to take this resource. If they go through this resource, it is taken. We only must limit number, because this resource, this narrow part of the street, is treated as common resource, and we must limit number of users of this resource. 1 truck, 2 vans, 4 cars, or 1 van and 2 cars. Okay? This is identification of resources. The manner of acquiring the resources, this resource, is to limit number of vehicles that can take the resource. 1 truck, 2 vans, 4 cars, or 2 cars and 1 van. And releasing the resource, we can allow other vehicles to enter the narrow part of the road on condition that there is enough room for them. So, in the beginning, for example, or when the narrow part of the road is empty, we just check if there's enough room. If so, we take the resource. If not, we wait. How many condition variables are needed? Different continuation condition is for car, 1 slot is needed. Different for van, 2 slots are needed. And different for truck, 4 slots are needed. So they check if they can take this resource, and leaving the resource, they know how many slots they release and compare with needs of the processes waiting, but of course waiting on different condition variables. Different for cars, because smaller place is needed for a car. Different for vans, because larger place is needed for van. And different for trucks, because the truck needs the entire narrow part of the road. Let us sketch the solution. Type. Yes? Oh, thank you. Okay, okay. Type road is a class. Oh, not condition variables, because we solve this problem using semaphores. But we just replace condition variables to semaphores, and we need one more semaphore for mutual exclusion. So I will solve it on binary semaphores because I think it is easier. It is for trucks, for vans, and for cars. And mutex. We have number of slots that are free. Initially 4. And initial values of semaphores for mutex is 1 and 0 for every type of vehicle, because they serve only for stopping the process. They do not count the resources. Okay. Wait. Enter truck. Truck or tier. Mutex it needs 4 empty slots. Yes. So if slots is less than 4, we can have many trucks waiting. So we need number of trucks waiting and number of every kind of vehicle waiting. So it's int number of trucks, initially 0, number of vans initially 0, and number of cars initially 0. So we increment number of trucks. We release the critical section to let other cars test, other vehicles test, and we stop on T until there will be 4 slots empty. When we are resumed, number of trucks is decreased. Okay. Now we know that we have 4 empty slots. So we assign 0 because we take them all. That's all. We cannot drive the car. Oh, truck, it can be, but we cannot drive a car inside critical section. Why? Because only one car can drive if we will use the resource inside critical section. So we must use the resource outside the critical section. Yes, please. Could you speak a little louder? Wait. Oh, wait is another name of P. Okay, you are right. T is better here. It's more consequent. Thank you. So we leave being a truck after some time. Mutex P slots. We free 4 slots. We release 4 slots. And we must let other vehicles enter the road. And I suggest that it could be a common function for every type of the vehicle. So I only will call release, and I will program this function later. Similar for vans. Similar, but not exactly the same, because the van needs 2 slots. So it waits on uppercase T here, and uppercase V here. One takes 2 slots, so it decreases number of slots by 2. And on leaf, it increments 3 slots by 2. Oh. And for car, enter C. It requires only single slot. Number of cars. It takes 1 slot and releases 1 slot. Okay. And now it's time for release. One comment is needed. This release function should be called only from other functions. It cannot be called from outside the class. It is not interface procedure. So we can, for example, prepare interface section in which we enumerate only enter and leave without release or similar. Because release need not be called from outside this class. It's a comment. Okay. Release. It can happen that a truck releases 4 slots and lets 4 cars or 2 vans to enter. So, in general, I think we should release the vehicles in a loop. So, while slots are 4 and number of trucks is greater than 0, we release a single truck and execute P on mutex not to run in parallel with the vehicle that is woken up. If in the meantime another truck approaches and this truck released by us left the road, again slot is 4 and we have a new truck waiting, so we can release it. We can signal it. But it is better not to favorize the trucks so much. So I will enter more general condition. Slots greater than 1 and number of vans greater than 0, or slots greater than 0 and number of cars greater than 0. If slots are 4 and number of tracks is greater than 0, we do the operation programmed before. Else, if slots greater than 1 and number of vans greater than 0, vans v mutex p, else if slots greater than 0 and number of cars greater than 0, cars v mutex p. And I perform it in the loop as many times as there is enough room and given vehicle is waiting. I signal this vehicle. It can happen that during this loop, new car will come, not a problem. If there is enough room, I can let this car. Okay. That's all. Okay. Okay. I check if all variables are initialized. Yes. Yes. And the comment cannot be called from outside the class. Okay, I will send it to you on the chat of this meeting. Okay. And the question is if we can solve this problem in a manner of occupying consecutive slots on the narrow part of the road. Just if the truck sees one empty slot, it takes it and it follows the vehicle that is already on the narrowed part of the road and follows it. I think it's possible. But on certain conditions. In this solution, we should treat the slots on the road as separate resources, and take those resources in a very strict manner. In this solution, it is not important for the first slot if it's a car or van or truck. Simply, if a slot is empty, we take it. But the difference lies in a manner of releasing the slots and letting other vehicles to take those slots. Let's try. We have binary semaphores, slot of 4. And mutex 1. We need to know how many vehicles are waiting for given slot. For the first, many of them can wait. For the rest, only, I think, one can wait. How to ensure that one waits? We can ensure by releasing the slots in very strict manner. So let us declare slot of 4. It is number of vehicles waiting for a given slot. I think that's all for variables, but we will see. We need a procedure to just to take a slot. Slot number E. If we need to, here we have the integer saying how many vehicles are waiting for the slot. However, we need to know if the slot is empty or occupied. So bool occupied of 4 is 0, 0, 0, 0, not occupied. If it's better to make a class that is a slot to solve it hierarchically. Let's do it. Type slot is a class. Binary semaphore S and mutex S0 mutex 1. Boolean occupied, initially not. And number of vehicles waiting for this slot. Waiting. Initially 0. Oh, here I enter void take. Mutex P. If occupied, waiting plus plus, mutex V, semaphore P, waiting minus minus. Oh. Then occupied is true. Mutex V. Oh, it's taking a slot. Void release. Mutex P. Occupied is false. If waiting greater than 0, mutex, semaphore V and mutex P. And finally mutex V. Oh. So we have a slot class, and here instead of 4 semaphores, we have slot S of 4 without initialization because they initialize themselves. Other variables maybe will be needed. I don't know if we want mutex here. Maybe not. Because if we are a truck, for example, take T, or better derive T without the slot number, is just 4 int E 0 to 3 because the truck must occupy the entire road. We take it is slot of I take, then we will release them in the same order. For int I 0, I less than 4, S of I release. So in the case of a track, it is easy. Drive car, the opposite extreme solution. We take every slot and release every slot. However, it can happen that on the road we will release slot number 0, for example. We want to take slot number 1 that is occupied, but we released number 0, so another car can take number 0. So we are in between of those two slots, 0 and 1. We should not let it. So we should first take the slot number 1, then release slot number 0. Okay, so it is not so easy. We take the slot. If E greater than 0, we release I number 1, I minus 1. And finally, we release the final slot. Oh, now it's correct. And for van, it is in between. So we will follow the structure of this function, drive vehicle. For every slot, we take this slot, but we free the slot that is not the second, but the third, because van occupies 2 slots. So if E greater than 1, we release I minus 2. And finally, we release slot number 2 and slot number 3. It's more complicated solution and hierarchical, because we have separate the resource of a slot. It is a true resource because on higher level, uh, we do not have any order of any synchronization. We have no semaphores here. But the matter is in the order of taking and releasing the slots. For the track, we must take all of them, one after another. Of course, no car can skip other car. However, for this issue, the solution lies in the order of taking. It is always taking the next resource with the number of previous resource plus one. So we cannot skip anything. I think that's all. I think that for students, it is better to use the first solution. It is easier to think over. And I think it is straight solution. This is somehow complicated, but I will copy this solution to your chat as well. Some students made the solution that I completely do not understand, and I will propose a time slot for individual students to discuss those solutions, because it is so complicated that I cannot imagine how it is solved, and you must explain me what is done in those solutions. Okay, let us switch to our lecture. What we talked lastly. Oh, last time we did not have internet connection, so it was without recording. Could you tell me what was the topic that we discussed last on the lecture before the midterm test? I think it is somewhere in paging. have we discussed I think that it was near interrupt on write mechanism. We discussed this, how the frame management is performed using interrupt on write. So I assume that we should start discussing the algorithms of swapping. Did we discuss them? Second chance. So can we start with clock algorithm? Okay. Clock algorithm is the screen shared? Yes. The mechanism is quite similar to second chance. However, first difference is that processes are not in a list, it is rather a cycle. So we can compare this to the list that is joined head to tail. And the frames are not in order of their loading to memory as in FIFO algorithm. The order of pages in the ring is arbitrary. It's accidental, we can say. But the mechanism is somehow similar. We have a pointer that points to an arbitrary page in a cycle. And if it is used, we clear the R tag and continue with searching. Because we cleared the R bit, we are sure that there is a page with R0 because we cleared it. So at last, after making a full circle, we will find a page with R0. It maybe other is with R0, we don't know. But if all other pages have R1, finally we will get our frame for the second time. Now it has R0, so we swap it. So working of this algorithm is somehow similar to second chance. Hardware least recently used algorithm. Least recently means that the page that was used mostly in the past, least recently. So we need to learn what page when was used. And there is a clever hardware algorithm for that. Nowadays, this algorithm is not used because in this algorithm we need a matrix indexed by pages in rows and columns. If we have, for example, up to 100 pages, 100 by 100 is 10,000. Okay, we can build such a matrix. If it's 1,000 pages, is 1,000 by 1,000, it is billion. So keeping million cells to perform an algorithm, it's not a good idea. But we will discuss it because it is interesting how it is achieved. Here we have the order of accessing the pages. Page number 0, 1, 2, 3, 2, 1, 0, and so on. After every access, the column of the page is zeroed, and the row of the page is entered once. But the row first, we see. So first we enter ones to the row, then zeros to the column. And it is done on every reference. Here, number 1, ones and zeros. Number 2, ones and zeros. Number 3, ones and zeros. Again, number 2, ones and zeros, and so on and so on. And we can interpret the content of a row as a number, binary number. This number is 8, 1000, okay? And which is recently used. We look for the smallest number. Here we have the row with all zeros, so the value is 0. This page was least recently used. Let's look from the last. Number 1 was recently used. Yes, number 1 has zeros. It's quite clever. However, it was used for smaller size of memories. Nowadays, we use least recently used software-based. Oh, let us return to previous algorithms. Algorithms require some hardware support. For example, both second chance and ring, so this clock algorithm, require to clear individual R bit. So the R bit is set by hardware. And we must have programmatical possibility to clear this bit. If not, we cannot build such an algorithm. So, given algorithms require given hardware support, typical support that is always implemented is clearing all the bits, all the R bits at once on a single write, clearing them all, reading them from hardware bits to memory in single step, not one by one, because it would cost much time to read them individually. So they should be loaded to memory in single step. And modified bit, M, should be cleared individually when operating system writes the content of the page to the disk, operating system clears the M bit for this individual page. So this support is in every paging system, clearing R bits altogether, clearing M bit individually, and reading R and M bits to memory in a single step. Sometimes it is more convenient, for example, if we can clear individual R bits, so we can implement a second chance or clock algorithm. Here, it's similar that we have possibility to read all R bits to memory in a single step. So if they are in such image, page 0, 1, page 1, 0, page 2, 1, page 4, 0, and so on. We have a software shift register for every page. We enter those values to the edge of those registers, 101011, 101011. And after some time, a typical real-time clock is used. So after a tick of this clock, we shift all registers one position to the right and read again R bits to this table. Of course, after reading this table, it is cleared to let the hardware set the bits for pages that are used. And it is performed after every time slice. So finally, after several real-time clock ticks, we have the history of R bit. For least recently used algorithm, we search for larger sequence of zeros in the beginning. Here, those two pages have 2 zeros in front of the shift register. So those two were used least recently. Let's look. Here they are not used. Here they are not used. Here they both were used. 1 and 1. Okay, and another algorithm, LFU, least frequently used, needs the same procedure for remembering which page when was accessed, but instead of the sequence of zeros, excuse me, we count ones. Which page has smallest set of ones, it is least frequently used. Here it is this page. It is least frequently used. Only 1, 1. Working set. Working set is defined by some time, and the time is represented by number of memory references, because in every time slot, it is just execution of a single step of instruction execution. So we can count time in memory accesses. for example, k memory accesses. The work set is set of pages accessed during that time. And we have an algorithm using this working set. It has it numbers the time slices in this computer. Current time slice is 2204. And in page index table, we have reference bit as usual, but additionally, we have when this page was lastly used. Of course, if it's 0, we leave it. If it's 1, we change the access time to current time slot. So after the procedure, all those pages will get 2204 in their last access time. If they are used in current slice. And we check the reference bit. If R is 1, we change the time of usage to current time slice. If a reference is 0 and the difference between this number and this number is greater than specified tau, which is work set time, we swap the page. If it's 0, but it was used in last tau accesses, we do not swap out this page. And of course, all R bits are cleared. This algorithm is just to divide the set of pages with R0 to two classes, in work set and out of work set. And we take the page from the set out of work set. If it is empty, we take from the work set, of course. Okay. And the last algorithm that I will not discuss with you is working set clock algorithm. Why I will not discuss it? Several years ago, I investigated the rules of this algorithm and I knew how it works. But it is so complicated that it is no sense to learn this algorithm. For sure, even if you will learn, you will forget quickly. It's very complicated. And I think it's only worth remembering the general rules. It is simply the algorithm that joins three rules. Clock algorithm rule, second chance rule, and work set. So I think that we can skip this algorithm, knowing that it has a circle of pages, that it clears the appointed page if it has R0, and in searching in a circle, it divides pages into two sets used during the tau last accesses or out of this set. This table is taken from Tannenbaum. And I think it is example how an engineer should not compare entities. Because looking at this table, how I can judge if realistic is better than good efficient algorithm or worse? Is big FIFO improvement better than quite expensive or worse? I think it is a good example how an engineer should not compare entities. Because I cannot draw any conclusion from this table. Okay. So we discussed page replacement or swapping. Two names are used for the mechanism. Let us discuss the set which is taken into account in swapping algorithm. What is the set of possible frames that we test for LFU or LRU or NRU, whatever? What is the set? So because processes compete for frames, and of course every program will have as large set of frames as is possible, and even if it gets smaller size of the set of frames, it needs to be enlarged during execution to better fit the needs of given program. Local and global. Local is a rule that every process has a set of own frames, and a frame to swap out is searched in this private set. So it's local because it's private. Global has general pool. Every page can be swapped out even if it does not belong to given process. Of course, it is if it contains a page, it is private. But when we want to swap out some page, we look for all the pages. Of course, if we would find an empty, we will take it. But if all are occupied, which is typical, we must appoint a single frame to release, and we take into account all the frames of all processes. Fixed algorithm, the name is misleading because it's not fixed. The name says that every process has a fixed set, but it is not the only set. that it can use. It is the private set, but additionally, we have some global set from which we add frames to sets of processes. Fixed can be equal or proportional to a size, or other circumstances can be taken into account. For example, number of page misses in time unit. So we have fixed size, a fixed set of pages, and general, we can say, spare pool for allocating to the processes. Quite often used is fixed prioritized, especially in real-time systems. If we need a frame for a process, a set of candidates is frames of all processes with priority equal or smaller to the current process. So a process can influence the speed of run of processes with lower priorities. It can slow down them, taking them their frames, but it cannot influence processes of higher priorities because it cannot take their frames. So in real-time systems, it is very often used algorithm, prioritized. We can measure how many page misses we have in a time unit, and typically operating system measure this rate because it can happen that operating system mostly deals with loading pages to memory rather than letting the programs calculate. Such a phenomenon is called thrashing. When the system loads and stores to the disk pages, and it does it so often that it is little time for calculations. This phenomenon, quite like starvation in synchronization, is not easy to discover because we must set some threshold. What is the number of accesses of page swaps that says that it is thrashing? We don't know. Even if we decide it is thrashing, how to liberate from this state, from this phenomenon? We have many page misses. How to perform to have smaller number? Easy solution is just stop some processes and swap out their pages to the disk of entirely all the pages of given process. But it is brutal solution. So it's not easy to fight this problem. Of course, miss rate counted per process can tell us how the process operates, and it can help us in assigning priorities to processes. Of course, thrashing process should get small priority. And even if we decide to stop some processes and entirely send to the disk, this rate per process can help us decide which processes should be swapped out. A smooth and flexible method of fighting this phenomenon is giving a process more frames. For example, having 200 frames the process trashes, so we will give additional 100 of frames, and we believe that it will help. It can help, and it can be that it does not help because of some unpleasant phenomena. This is an example of most well-known anomaly called Belladis anomaly that shows what could happen. It is, we can say it is academic example because nowadays FIFO algorithm is seldom used. Typically, LRU, LFU algorithms are used, not the FIFO or second chance. So, taking from this perspective, we can say that it is a theoretical example, the academic example, but it clearly shows what can happen in some special circumstances. How to observe this page, this table? This the column of this table is a queue of frames. The column, and consecutive rows are time slices. Okay. In time 0, we have empty queue. No page is loaded. And over the table, we have numbers of pages that are accessed. We have access to page 0. So page 0 is loaded and it is in the head of the list. Then page 1 is needed. It is loaded, it is in head, and page 0 is moved lower in the queue because in FIFO method, at the head it is the page loaded recently, in the tail mostly in the past. Number 2 is accessed. Again, we have 2 in the front, 1 and 0. Because in every row in which we don't have a page that is accessed, we have a page fault. It is marked P. Totally, we see that the history of loading pages says that we have 9 page faults. Almost every access to the page reports page fault. For in this situation, not, because we have access to 0, but 410 are in memory, so we just access without loading page to memory. But only 3 accesses are free from page fault. So operating system decides this process operates poorly. Let us enlarge the set of frames that this process can use. So we give it 4 pages for this second execution. And what we see, for 4 pages, we have 10 page faults. It shows how it could be hard to fight thrashing. Even if we provide better environment for a process, it could operate worse. This is called Belladis anomaly. Of course, there are other anomalies, more subtle. I try to find them, but I think that because Belladis is so widely known, they are not described in the literature, I think. Because I couldn't find names of other, because they do not have names. What is important in systems like Unix? We have page index tables. During the operation, the MMU loads page index tables to its cache to resign from one additional memory access per every effective memory access. Excuse me. But when we perform a context switch, this cache is cleared. Not only this cache. What is the name of associative memory for paging? Translation look-aside buffer, TLB. We talked about this. TLB is cleared as well, because for another process, we don't want those accesses to remember. So generally, you must know that context switch in modern computers is extremely expensive, because not only we should store the registers of one process and load registers of another process, but several algorithms that speed up the execution of the program are cleared. For example, return stack. We have, we discussed how the stack is built of the process, and every stack frame contains a return address. To speed up the execution, the return traces are additionally stored inside processor on separate stack. Such a way, return does not require access to memory, return from a function. It takes the trace from internal stack in a processor. However, when we perform context switch, we don't know this additional stack. It is built for another process. More. Loop counter. Because of changes in the pipeline, jumps are most expensive instructions to execute. Having several percent of jumps in the program, example 5%, can double the execution speed of a program compared to the same program without jumps. So we can have a loop counter if we have a for loop in the program. We always know how far we are from the end of the of this loop, because we just can count the terms of this loop. If we have this counter inside the processor, starting a turn of the loop, we can tell if the loop will return to beginning or we will get out of it from this loop, because we know if it is final value or not. It speeds up the execution. Jump prediction. If we have conditional jumps and we can guess if the jump will be taken or not based on values, but we can predict correctly or not. So, basing of the behavior of the process, special jump predictor can tell us if this jump is probably will be taken or not taken. It builds some structure in hardware. Again, if we perform context switch, we must clear the predictors, and so on and so on. We have many hardware mechanisms that speed up the execution of the program. And generally, they analyze the program and remember some properties of the program. All this must be flushed out when we perform a context switch. So a new process after context switch performs quite poorly until a processor will learn the operation of this process and will switch on the mechanism for speed up the process. So we must say that context switch is extremely expensive. So if we have a program that is shared, for example, we have many copies of shell when you are in laboratory. The students sit at the terminals and they run programs, and every student uses 1, 2, or 5 copies of shell. This shell is only once loaded to memory, the code of shell. So if we flush out the page index table from the cache in MMU, we will load the same after context switch, because it's the same program when we switch from shell to shell. So it is better to have a tag, special tag, if it's shared and discover. If we switch from one shell to another shell, do not clear the cache in MMU. It would speed up very effectively. It will speed up the execution. Okay, that's all for today. Yeah. Don't you have a catalog for your solutions?
Said from the laboratory presentation previous week that how we
Isn't it written in the chat how you should name your solution? If not, I will explain it.